Thank you very much for coming. I know it's like not great weather outside, so it's good you came. I'm an assistant professor since March at a place called IDC Herzliya in Israel. Because you probably don't know about it, it's a small institution. I'm going to start by telling you about it. So this is what it looks like. It's by the beach. It's beautiful. The weather is always nice. It was 25 degrees when I left, and I think it still is. It's a small institution. It's been started in '94. So the idea was to build a university that would have a very different structure than the usual Israeli universities. We have 28 labs and research institutes, and it's ranked #1 in terms of students' preference in Israel. So what happened is this university has been built really to think about students and education and a very different way of thinking. So right now we have students from undergrad to masters, and we're working on building a PhD program. So it's still growing, and it's actually a pretty exciting place to be. So we have about 1,500 students, so it's very, very small. I was at Stanford before, so it's a totally different scale. We have 84 nationalities, and this is pretty special because for a very small campus in a tiny country to have people coming from all over the world, it really makes it a very diverse and special place. There's a lot of activities and things that students can do, so there's about 56 plus projects they can do, and it's a lot of fun. So you probably already know about HCI, but I'm just going to give you a definition just in case, so we're all speaking about the same thing. So I think about human-computer interaction as being at the intersection of computer science, social sciences, and design. My specific area is around computer science and design. My degree is in robotics, and then I moved into computer science. But during my postdoc, I moved more into the design side of things. And what I'm going to show you right now is very much going into the design space and opening it, so then we know what to actually build. Sometimes we just want to build something, but we spend months doing it, and we don't build the right thing. So by having the opportunity to actually think about the design space first, we're sure that we do it in the right way after. So these are user interfaces. So basic UI, just so we're all on the same page. Once again, you've all seen that? Yes? If you're telling me no, I'm missing something. Okay, so all seen that. Okay, so here, depending when you were born, you may have seen the one at the top right. Maybe some of you haven't seen the one at the top right. But it's a very specific desktop environment. It means you walk into your computer, you usually sit down to use it. Usually you type on a keyboard, you use a mouse, and then you get a screen for feedback. Yeah, totally familiar, you can follow me here, good. Okay, so now what has changed? Because now we have different devices. So if we look at our new devices, who here has like a smartwatch? Not many of you? Yes, couple? Okay, so if we're looking at those devices, they're very different. They're portable, so they come with you. So it's not about you just walking to a space and sitting down. It's about you carrying this interface with you. But now if we think in terms of interaction, we still have a screen. We still have graphical user interface. How do we do input? Touch. And if we want to type, what do we use?
Voice.
Sorry?
Voice.
Voice sometimes. What else?
Fingers.
Yes. And what do we do touch on if we want to put text?
Virtual keyboard.
On a keyboard, virtual keyboard, exactly. So basically, we went from having a physical keyboard to a virtual keyboard. But if we think about it, apart from touch, not much has changed. And it's a little bit frustrating. It's like we've made so much advancement in computer science, but in terms of interface, it really hasn't moved that much. So a lot of my research is like thinking about how do we go beyond? How do we think about interfaces differently? And the reason for that is that we don't live in a bubble. It's just me in my bubble. We live like that. So for example, here this person is waiting for the bus and texting. Here people are sharing their screen with friends, maybe sharing pictures. This person is texting at the back of a motorbike. So we're using differently. In Israel, you even see people texting at the front of a motorbike, which you probably don't see in Canada because people respect the rules, but back home they don't. But it's pretty dangerous, but people still do it. So we really have to think about how do we adapt interfaces to everyday life so it becomes safer, it becomes more interesting, we can do something different than what we can do now. So I'm going to show you just a little vision. So this is not implemented, it's just a vision. But if we think about future mobile devices, and they could look like drones, how do we interact with them? I can't have just a keyboard the same way. So how do we rethink about interfaces? We'll get back to that video in a bit. I just want to give you a little advance to what's going to happen. But basically, my research is about designing, developing, and evaluating novel interaction techniques and applications for mobile devices. When I talk about mobile devices, here's how I classify them. So first we have fixed interfaces, so anything with desktop. We have carried interfaces, so something I have to bring with me, like a phone. We have what I call on-body, because if something is like a wearable, like a watch, you don't use it the same way you use a phone. Your phone, you can put it down and use it. Usually a watch, you have it on you. So already you can't use both hands the same way. So we have, even though it's very similar, you still have to think about the interaction in a different manner. And then out of body, because what happens when you're mobile, but the device is also mobile? So you're both mobile, but maybe not at the same time. So how do you create an interaction that makes sense in those situations? So to me, mobile devices are all of these. And when I talk about mobile, this is what I mean. During my PhD, I mostly worked on carried interfaces. I was going to tell you a little bit about it, but just for sake of time, I think we're going to skip that part and really focus on the on-body and out-of-body. So I'm just going to skip that very quickly. It's not as interesting. Don't worry, you're not missing anything. Okay, so now we're going to talk about on-body. So when I started working on on-body interfaces, we started thinking about context-aware smartwatches. So one of the problems of having a small screen is you can't have anything and everything on one screen. Yes? So on a computer, you can have multiple desktops, you can have like, there's lots of options. On a very, very small screen, it's harder. So there's this concept of context-aware smartwatches where, for example, if you're running, you can see your run stats. If you start getting a phone call, that takes over and you can see who's calling you. And then you have just a different interface that changes based on what you're doing. So we're using sensors. And so this was just a concept, but this is like totally realistic. But now if we think about it, context is wider than that, and it matters. So for example, here we have this person biking and looking at their phone. It would be the same for a watch, and they missed it. Okay, so what happened is we could actually use haptics. So we can use something different that I don't have to look, so I can keep my eyes on the road. And it's actually also important in different contexts. Like here, the person is in a meeting. They may want to get some information, but they don't want everybody to see that they're looking at their phone because it's rude, different reasons. But in both contexts, the person cannot put their eye on their interface. So now we were thinking about context in terms of activity, but context is much wider than just activity. So we were trying to think about what can we do by using haptics. And so one of the things we were interested in is thinking about progress monitoring. So for example, if I want to see how well I'm doing in terms of health, for example, so something like your Fitbit, that's telling you how many steps you've done, how close you are to your goal. And we were thinking, okay, in that case, it could be really cool to have vibrations. Because maybe I don't want to check all the time. Maybe I'm busy, I'm doing something else. So we wanted to use vibration and see if that would encourage people more. If I keep getting information about how well I am doing, is that motivating me more? And when we started to do that, we realized that there wasn't really any good system to encode vibrations. So there's a ton of research on encoding vibration with multiple motors and doing something quite complex and getting different sensations. And you have this project that looks at like giving you a sense of touch, giving you a sense of pressure. And it's really interesting, but it's pretty heavy equipment. And if you think about wearables today, they get very, very small. And they have one actuator that's really, really cheap. So you can't do much with it. And actually what we realized is there was very little work in terms of just different signals from one single simple actuator. All the work was about really complex systems, and it doesn't work with today's wearables. So we were trying to think, okay, how do we push the boundary of creating some sort of vocabulary that I can understand on a single actuator? So I went back to my drawing boards and back to basics. And I was like, okay, let's think about how we can encode the vibration. And again, there's a lot of research on that, so we just used some of the research. So it could be temporal, it could be in terms of vibration. So here, every little squiggly line is a pulse. So here you would have, for example, number 1 to 10. So 1 vibration is number 1, 2 vibration is number 2, 3 vibration number 3, etc. Here it would be a matter of time. So shorter or longer vibration to encode a number. Here it would be like in terms of time, and then you would have a little counting that happened. So it would always take the same amount of time, but then it would be encoded with in different ways. So we just decided to go and test it and see what would happen. So all of that was done indoor. And we found out that the last one at the end, so this one that works like a Roman numeral system. So it's 1, 2, 3, 4. Then 5 is a long vibration, and then it's 5 plus 1, 5 plus 2, 5 plus 6, 3, I can't count anymore, never mind. And this is how it would work. And this one we had 96% accuracy in the lab. And so the idea was just to create a very simple system to give you numbers 1 to 10. We were thinking if we're doing behavior change or fitness tracking, it could be like a percentage. So 1 is 10%, 2 is 20%, etc., etc., to 10, 100%. We didn't want to encode number to like 10,000. You know, it's not about knowing exact time. It's not. It was just to know about how am I doing, and I don't need to check my watch. And if you think about the earlier Fitbits, for example, they just show you a dot. It's a dot, and then 2 dots, and then 3, and then 4, and then 5. So we weren't quite off. Like this was pretty much what people were doing. This is how it worked in the lab. This is how we tested. So the person would learn the number, so they knew how it would work. They would get the vibration and then tell us what number they felt. In the study, they didn't have the sheet of paper in front of them, but it's just for the video to show you how it worked. So with that, we get 96% accuracy. So that's pretty good, right? 96%. Okay, what's the problem with this study? Or what is the limitation? Sorry? Indoors? So what's the problem of being indoors? Yeah, so basically there's no noise, they're focused, they're happy to be here, you know, they're good to go, they're like ready for it, they get the vibration, it works. So now the question is, how do we validate that outdoor when people are actually doing other things? So what we decided to do is first to validate whether the vibrations could be felt and could be understood properly. We didn't want to directly go into a study where we'd study number 1 to 10, because then you have the progression and you're able to know. We wanted to know if the system worked. So we recruited 22 people. They did a 4-week study, so over summer. We had people from 20 to 69-year-olds, so it was a pretty wide range of people. They all had different jobs, different timetables. We tried to only have people that worked during the day, because the study would take place between 7 a.m. and 8 p.m. They could remove the band at 8. If they woke up later than that, they would just miss their first vibration, then that was fine. The idea was not to like wake them up and annoy them. The idea was to make sure that they could understand. They would get up to 12 vibrations a day, and we had a compensation scheme that was designed in a way that people would be incentivized to wear the device, but it wouldn't change how they would want to perform. So here, for example, you have the same lady, she's getting the vibration, and then she's actually working on it, and she can attend to it. The way she attends to it, how we're getting the data, you can see at the bottom. So she can say, no, I felt the vibration, but I have no time to answer. Or I felt it, and here is the number that I felt. So it's very simple button press. Then she says, sure she is of the number she felt and what she was doing at the time. So it's a very, very simple way of gathering the data that doesn't take time out of people. And at the same time, if you're doing something else, like I'm talking to you, I don't want to look at my watch, I can just even press that button, say I felt it, but I can't do anything about it. What we did is every night there was also a questionnaire that would get, that was generated on their computer, and they would get an email about it. And basically we tell them, for example, you had a vibration at like 7:45, you didn't answer, what were you doing? And so people would tell us, today I woke up at this time, I did this, or I remember I got a vibration, but I must have been under the shower. So we would get a sense of why they were not getting a vibration or why they didn't reply to something. Anyway, after 4 weeks, we found different things. One of the things we found is that 67% of the time people said they were sedentary. So we took a wide range of people. We had some people that were exercising a lot, people that were exercising not very often. But what we found is when you exercise, it's usually, even if you do it 2 or 3 hours a day, then the rest of the day, you're not exercising. And so we found that people are actually extremely sedentary. Even people who feel they're very active, who walk to work and everything, the rest of the time you still like sat at work or sat at home. And so people were like, they couldn't believe how often they were just stationary. One thing they told us is just by having to answer they were stationary, they wanted to do more and change their behavior. They felt bad about saying it. They were telling us I didn't want to write it. Some people said I was really hoping it would vibrate while I was doing something, because I really didn't want to write sedentary again. But that's interesting. So the other thing is people were often walking. Other is a range of things. People would say I was putting the kids into the car and it vibrated, so I didn't feel I was doing anything, but I wasn't walking, I wasn't sedentary, so they would use that. Some people said they were cooking, for example, and then it would just vibrate, and again, they didn't know what to use, so other was for that. Driving. So driving is an interesting one, because most of the driving, we got it while people were actually doing it. And so we had that during our pre-study of a week, and I asked people, I said, well, were you like driving and doing it? And they were like, yes. So then I was like, okay, we're gonna get in trouble. Like if anybody gets into a car accident because of the study, this is not good. So then we made sure to explain to people for the main study, like, by the way, do not ever put yourself in danger to answer that. This is not, it's fine. If you can't answer, you can't answer. If you miss one, you miss one. We also give them the ability to not answer and then go back and answer like within, I think, 10 or 15 minutes time frame. So they could always go back and give the answer later if they couldn't. And so what we found is in the main study, after all of that, we still had 7% of the people saying they were driving. And I asked those people, what were you doing? So some people said I was at a stoplight, I was waiting, I was blocked in traffic, which, fair enough. But some people said I was on the freeway driving, and the freeway in California that was done at Stanford, it's huge, it's a lot of cars, it's like 7 lanes coming from every direction, and they were doing it. And so I started talking with these people, and I realized they actually text and drive. So they didn't think that was any more or less dangerous than what they're doing, so they didn't even think about it as being dangerous, and they were like, no, it's totally fine. And so it's really important here, because what we find is that we have technology to support people better. So for example, when texting and driving, you can speak instead of using text. Still, people text. So what do? We put regulations, and we say, no, you can't do it, and you're gonna get a ticket. And the tickets are expensive, but people still do it. So it's really our responsibility when we build those interfaces to think about people. You can't just expect people to just stop using it. This is not what happens. So you have to make it safer. Sleeping, so that we got from the other questionnaires, we did not wake them up. Some running and some cycling. So as a result, we got 96% accuracy and 89% in situ. So 90% in situ is pretty damn good. But it's also has limitations. So for example, if we were to work in a hospital and to give vibration as an error code, we can't have 10% mistake. It's not gonna work. But now the resolution of our study is about, we have 10 numbers. Usually when there were mistakes, it was between 8 and 9 or 3 and 4. So it was for the higher numbers. So what we find is actually, it's possible to reduce that gap by having maybe less numbers and then bring it up again. But it's still pretty good. And for something like what we want to do, which is about behavior change, because you know that after 8 you got 9, you get a sense that you did better and that you move forward, and actually it doesn't really matter. So this is pretty good. Now we looked at the distribution per activity. So what's interesting is running does very, very poorly. And what happens is, because when you're running, you feel the vibrations from the ground, for example. And so people would say, I felt the vibration, but then I felt the vibration from the ground, and I just didn't know what number I felt. They just couldn't do it. And so what it tells us is maybe we need stronger vibrations when people are running. Or maybe we just can't use vibration when people are running. And that we don't know yet, and that's some things we need to check. But this is part of the question we highlighted. All the others do pretty well, and actually stationary does the best. So I'm just like talking to you, and I'm stationary, and it works best. So here it's interesting because it works best 70% of the time. So most of the time people are stationary, and most of the time it works well. So the systems of like giving vibration to convey information to people is actually pretty sustainable. Okay, so the other thing we found is that the social context had an impact on the recognition rate and the comfort. So for example, I'm talking to you, it vibrates, it distracts my thoughts. And so people would report, for example, I was talking with my boss, and then they get upset or they get distracted and they would not want to show they were doing it, and actually that totally damaged the process. And this is really also interesting because most of the sensors right now look at activity. When they look about context, when they think about context, they look at activity. But very little sensors actually looked at social context, and when it mattered a lot. So now what we can do is think about the sensors we want to design next. And maybe we want to design sensors that are going to just pick up with a microphone how many people are speaking, or who are the people speaking in the room. And then we can decide what to infer. So it just opens up the space of like what context we want to look at. So what did we learn? We learned that different vibration patterns can be recognized from a single actuator with high accuracy, low mental demand, and they were not disturbing people. So they had up to 12 vibrations a day and they were fine with it. They didn't get any notification on the watch. It was totally separated. The activity mattered, but the social context mattered too. So then our next step, and this is something we've done part of it already. So one of them is to look at discrete input and output. So what if I just use my hands to get data and then I get the output on the watch, for example? Another thing we did is actually a very big study I conducted last summer, but I still haven't written it up. I finished my postdoc and then I got busy and I started my faculty position. So I have this huge study that's a 6-week study that is not written up yet, but I'm working on it. But basically what we're doing here is we spent 6 weeks with 45 people. They were, I think, from 18 to 70 years old. And we wanted to know if we can give them information visually, by vibration, or both, and if it made a difference. So it was used as a step counter, and every 10% of their goal, they would either get a vibration if they want that condition, they would either get like just some visual information, or they would get the vibration and visual information, depending on which group they were on. What we found so far, and I'm still, again, analyzing the data and putting it all together, is that it made a difference. Basically, the way you convey information to people makes a difference to how you perceive information. And that's really novel, because right now we're really thinking based on the context, based on what we're doing, we're going to give you information one way or another. So for example, I'm driving, maybe I can get vibration, so I don't need to read. But actually, it matters more than that. The way you're getting the information, you interpret it differently. But that will be for the next talk. Okay, now I'm going to tell you about out-of-body interfaces. I just want to give you a taste of like different projects. So we'll talk about drones a lot. When I talk about drones today, this is this type of drone, nothing bigger than that. So I'm talking about the small commercial drones, like for example, like this one taking pictures. They can be used by journalists, for example, to find out what's going on, to see the size of a crowd, for example. This is a design project where they're looking at using the drone in case somebody has a heart attack, so the drone can come and support them, or for delivery. And we're all familiar with delivery and waiting for the drones to deliver within half an hour so we can get our goods right away. So one of the questions about drones is how we interact with them. So this is one potential interaction technique here for filming. It looks complex. It is complex, one of them. This is another interface. It looks easier. It is easier, but it's still like not straightforward. So right now, for example, here you have your phone. It tells you the battery level. It tells you what you're doing. It tells you where to go left, to go right, what is the altitude, the speed, the battery. So you get a lot of information on one little screen. But now, if we use this phone as a remote, does it really work? So for this scenario of taking pictures, it works pretty well, because you just control your drone. You go and you click on the picture button, and you take a picture. Here, it gets harder. It gets harder because maybe I need to know where the people are. You can see here some people trying to reach. So then you need some extra information that you may not have on your basic interface that works great when there's nobody around. What about this one? How do you use your phone? Difficult, huh? Really difficult. So we're not quite sure. And this one, to me, this one is actually the hardest. Because let's say this drone comes to deliver, and it's not for you, it's for next door neighbor. How do you tell the drone to just go away? Because if it's your drone and you're waiting for it, you probably have the app, and you can maybe like pair it, and maybe you go to your app, and it's fine, and it's organized. But if it's not for you, or you don't want the product, you don't have any way to communicate with it. So what do? You download the app from that company, you wait for it, you look for the right thing, 20 minutes later you're still there. So it's really not obvious how we are going to communicate with these devices. So they're coming into our space, but then what do we do with them? And basically, we're really good at having this distant interaction. So whether the drone is semi-autonomous or fully autonomous, we're really good at doing that. We know AI very well, we can plan a path, we can tell the drone to go from point A to point B, we can give a GPS positioning. We're good at that. That works really, really well. But now the question is, what happens when the drone is next to you? And it may or may not be your drone. If it's not your drone, it comes next to you, what do you do? And so some people have some clever idea, and I always like people with clever ideas. It's very thought through. So they tell you, okay, we can do that, we can have a drone delivery, sushi, and this is actually videos you can find on YouTube. They're actually really funny and a little bit scary. But basically, it's like this drone comes and delivers. Okay, so I want to pick up my sushi. And if we think about it in terms of mechanics, and I'm able to calculate that, right? I'm able to say, okay, like what is going to be the flight, the position of the drone based on I'm removing some weight. But in terms of the lady, she has to put her hand over 4 propellers, and it's pretty scary. She could hurt herself pretty bad. And in the videos, you see the drones going very close to their legs. And you're like, oh my gosh, no, it works. So it's like people propose solutions, but they're actually not necessarily good solutions. So now we really need to think about, how do I do when this drone comes to me and I want to just like do something with it, but in a safe manner? So what I'm saying is that we actually need natural human-drone interaction. We need to support people who've never seen drones before. We're not very technology-oriented to be able to use them. Because if they come into our environment, I need to know what's going on, and I need to have some level of control on it. So for example, here, this person, let's say, is walking in a park, and a drone comes over. Yeah, that seems like a scenario that would make sense. You could see it here. But then maybe they don't feel comfortable with it. How do they get the drone to stop? It's not their drone. So what I did is I started by an elicitation study. So are you familiar with elicitation studies? Not? Okay. So elicitation studies are basically something that was invented for the new technologies that came out. So for example, something like the interactive tables. So they created those tables that were with a computer on the surface. It's called, like nowadays you have the Microsoft Surface, you may be familiar with. And we didn't know if people would use them as a table or people would use them as they use computers. So it was really not clear what people would expect. So what we did is the same thing. We just asked people, how would you do this? And from that we learn how we need to design the technology properly. We did what is called a Wizard of Oz. So it means the drone wasn't fully autonomous, but we would control it in a way that people felt the drone was reacting to them. We gave them 18 tasks and we recruited 19 people. So we had lots of tasks. Some of them were very simple. They were just like stop here, land here. And some of them were very complicated. So like take a picture of this or take a selfie with the drone and trying to see how that would work out. So this is what people would see. So we didn't give them any verbal instruction because we didn't want to bias the way they thought about the technology. So if I say, tell the drone to, by using the word tell, I'm already conveying some information that maybe you need to talk to the drone. And we wanted them to do whatever they wanted. We wanted to see if they would use gesture, voice, if they would take their phone. We just wanted to see what would happen. So we gave them an action, a start state and an end state. And their goal was to get the drone from the start to the end. Very, very simple. So here the action is called stop by me. And they would need to get the drone that is coming towards them to stop close to them. And here you can see this lady, she extends her arm and she says stop. This is another one, it's called side. The drone is at a location and then it's a bit further to one side. So here she extends both arms and she feels like she's moving the drone. So I'm going to show you a very short clip of what happened during our study. I want you to pay attention to the gestures, but also to what people say.
Stop. Stop. Drone, stop. Hey, boys. Here. Come here. Drone, can you take a picture of that palm tree, please?
Okay, did you notice how you said please at the end? Okay, so basically there's a lot of things inside it. So nowadays it may seem normal because you may have seen some drones in the last year that use exactly what we did. But this is what happened when you publish your work and don't protect it. It happens in product. Maybe it's just luck, I don't know. So we found several things. So we found that some of the gestures had a high agreement rate. So what does it mean? It means that despite the fact that none of those people had seen drones before, used one before, they decided to use the exact same gesture to command the drone. So here, close would be a beckoning gesture, and far would be a pushing gesture with both hands. So selfie is a really good one. And again, 2 years ago, that was very different than what it is today, but nobody would have thought about doing this gesture. Like if we were to design the system ourselves, we wouldn't use that. But then what happened is we realized that people didn't have any way to frame. And because they didn't know how to frame, they basically used that to frame where they wanted the selfie to happen. So they took from what they knew of using a graphical user interface on a phone for framing and moved that into the gesture space. So it's a gesture we never do. But they still decided to take this one. And it's funny because all of them used the very same gesture. One thing we found at the beginning is that people would do that and they would just like smile and wait. And it was a Wizard of Oz. We weren't actually doing it. There was no camera on the drone. And they would just wait and smile. And so we realized they were very engaged with it. They totally believed in it. But then we also found that we needed to tell them the photo was over. So what we did is we installed some sort of nod gesture. So the drone would go down and up saying, okay, I saw you. You had a question.
Yeah, it's interesting. If I thought about a gesture for a selfie, I would have just used one hand, right? I wouldn't think of this bottom hand to do that. I would have just thought of the one hand.
So most of our participants use this gesture. A couple, I think, I can check the numbers. I think they're in the paper. I think a couple use this, the clicking. But it was very, very consistent that the large majority of people use this one. Okay, so now what we know is when the drone is coming like this towards you, you could just say stop. So I'm going to tell you more about the results, but before I move on to that, we were wondering what would happen if I do it in another country? Because there may be some sort of cultural bias. So when you do this type of studies, there are different biases. One of them is the group of participants. So in our case, we used young Stanford students. So there is a bias there. But at the same time, they're what we call the early adopters. So they will be the people who buy this technology first, start using it, and then inform other people of how to use it. So we accepted that this was a bias, but that it was an okay bias for this study. Like nothing is perfect. You have to make some choices. So this is a choice we made. But the cultural one was important because now we're selling technology for the whole world. But does it work the same way for everybody? So we wanted to see how the other cultural influence would actually change how people interact with the technology. And we replicated the exact same study on a campus in Shanghai. So same type of population. So here you have some little samples of how people actually interacted with the drones. So very similar in some ways. So one thing we found is people got very close to the drone. We already had that in the US. But this is very, very close. And this is very dangerous. But people feel very comfortable with the drone. So you'd think, as new users who've never seen a drone before, it's pretty scary. But no, it's very exciting. So people get very close to it. The other thing is this one. Okay, so I don't know if you can all read here, but basically he says that by using one hand, it looked like he was being rude to the drone. So the same way that person in the US said please, here we're having someone in China saying that he doesn't want to use one hand because he feels rude. And yes?
Well, and also the one in America, one man kind of treated like a pet.
Yeah.
Like your boy.
Totally, totally. I'm getting back to that in a second. But basically, the thing is like, so for example, in China, people give with two hands for politeness. And so here he's saying the same thing. He's saying, I need to use both hands to be polite. And this is not how we treat technology. I never say thank you to my phone. Maybe I'm just rude, but I never be like, oh, thank you for working so well today, or to my laptop. But people are doing that to the drone. This is not how we use technology. Do you ever say thank you to your computer, to your TV, to your phone? You're so rude, you see? Canadians were supposed to be really polite, and you see, even with technology. Okay, so now this is the other thing. Look at this one. Can you read what's at the bottom? Okay, so here she's explaining that she actually gave instruction to the drone to go higher because she wanted the drone to be happy. So they're actually really adding emotion, they're adding like feelings to what the drone is doing. And again, this is not the normal way we use technology. Okay, so what we found, and it's very quick, I mean this is a Kai paper from this year, so I'm just gonna go very, very quick on it, but you can read the paper if you want more information. We found there were many similarities, but there were also specific differences. So for example, we'd have the same thing about the stop sign where there was a high agreement, but the sign was a different one. So in China it would be this sign. So it was high agreement, but different gesture. The other thing we found is the way people use multimodality was different. So for example, in the US, people would say, come here. But then the gesture would be the same thing as what they said, same signification. In China, they would use a gesture and the voice combined differently. So for example, they would say, go. But then where they were pointing were the place they wanted them to go. Or stop. And then the gesture meant here, the position. So it was combining. And again, it's interesting because if we build sensors, we usually only build for like gesture, or we build for voice, or we combine them together. But we don't look at how to put them really like fully, truly multimodal in a way that I'm gathering data from both. So it informs us on how we want to build this type of technology. It also shows us that if we want to build something that's going to work for the whole world, we may need to adapt. We can't have this gesture to be the same for everyone. It's a different country, it's a different gesture. And so that's something we have to take in consideration. So our main findings were about the interaction. So that's from the numbers are from the US, but we have very, very similar findings from China. But we had 18 out of 19 people who at some point talked to the drone like if it was a person. They often talk to it like if it was by proxies. They would say, oh, it's like if I'm helping my friend park their car. Or I'm asking a group to move so I can take a picture. And 16 out of 19 we talked about it like if it was a pet. So people use a lot of he, talking about the drone. More he's than she's, but they would not say it. One person kept calling the drone Nick the whole time. And you know, when you're running these studies, you have to stay serious because you can't make fun of your participants, first of all, for a ground rule. You have to be like professional and you have to like acknowledge that they can do whatever they want. And so you have to stay serious to the whole thing. And I can tell you many times, I just wanted to laugh. You know, I just wanted to just stop, laugh, take a break and come back. And so at the end of the study, I asked this person, why Nick? And he said, well, it's my dog's name. And it seemed so normal and obvious to him that this was the right way of doing it. And this is really, really powerful because, again, we don't use technology this way. But now that the technology moves, and I think it's really this notion of animation, people take it very differently. And we have a lot of research on robotics and ground robotics. But what we're getting are different results from what they have in ground robotics. And again, it's different. So we have to redo a lot of the research they've done to understand how it applies to drone. And so drones are like in between. They're in between robots and mobile devices. And so we have to think about them very, very differently if we want to integrate them safely into our day-to-day lives. So the thing about safety, people were more worried about the drone safety than their own. And they would constantly talk to us about being worried the drone would get hurt. Not damaged, broken, hurt. And so one time my student, so I had my student piloting the drone, and she got the drone to hit the floor. You know, it happens, you just pilot it, you go a bit too fast. And the person went to apologize to the drone for giving an order to go too fast on the floor. And it's just amazing how engaged people were with it. People get very, very close to the drone. Those are the numbers from the US. In China, people got even closer to the drone. In the US, we had one person trying to touch the drone. In China, when a person like the one you saw physically grabbing the drone, but people got very, very close. So those are HAL's proxemic zones. So this is research from psychology from 1963, and it's looking at how close we are when we interact with people. So the idea is right now I'm talking to you, you're pretty far away from me, this is a public space. And then if we were talking one-on-one, we may be into the personal space, but the private zone is really just for you and your close ones. And you know how sometimes people get way too close to you and it's uncomfortable? It happens on the bus, on the train, and you're just ooh. This is it. It's because they get into your private space. This is not a zone where they're supposed to be. So those change by culture. But what's interesting is people got the drone. So 16 out of 19 participants at some point in the study chose to get the drone within their personal space, 3 feet. Out of those, 7 got them at 1.5 feet. 7 people out of 19. It's awfully close. It's that close to your face. But they were very, very comfortable with it. They had the choice. They were outdoor. They could move back. They could get the drone to go further. They chose to be that close. It generates wind, it generates noise. They still chose to be that close to it. So it tells us different things. It tells us that, first of all, we need to build much safer drones, because right now it's not safe. And during the study, a few times we got really scared, because we didn't want to bias the study. If we stop getting the drone closer to them, then it's the drone doesn't obey them. And so it biases our study. But at the same time, if we hurt someone, we're responsible. And so it's this very, very fine balance when you're running this study of hoping it's going to go okay and you are not going to do anything crazy. But the thing is, how can you expect to remote control the drone if you have it that close? We never use remote or phone or anything if I can touch something, right? So if I have it that close, I need some sort of direct manipulation. And the other thing we found was about feedback. So people wanted to have more information from what the drone was feeling, how the drone was doing. They asked us for lights. They asked us for the drone to speak back at them. So they'd say something like, oh, I told the drone to do this, and I would have liked to get a response from the drone. The other thing they asked is for eyes. There was no eye on this drone. I can guarantee you that. There was not even a camera on that drone. People still felt that there was, because of the lights on it, they felt that there were some sort of eyes and that the drone was looking at them or not looking at them, and they were feeling very strong about it. And so they kept asking us for eyes and how the drone, just acknowledgement to what the drone understood, to what happened, etc. So we took that further. We're okay, so if they want feedback, we're gonna give them feedback. I didn't want to make it mechanical, because what happened is people thought about it like a pet or person, and the way we communicate with each other is not through blinking lights. Not till now. So we can perceive things when we talk to each other. So we started thinking about how does it work with animals. So how many of you here have a pet? Goldfish don't count. Okay, so if you have a dog or a cat, how do you know that it's hungry? Okay.
Sits by its bowl.
Okay. How do you know it wants to go out?
Sits by the door.
Okay. So from its behavior, from the sound it makes, it doesn't speak to you. Maybe it does. It's not supposed to. But it doesn't really speak to you. But there is some sort of body language, there's some noise it makes, and you understand some information from it. So we wanted to see, okay, if people are going to be considering the drone like an animal, can we use the drone's behavior the drone's flight path to actually convey some level of emotion, of understanding of what's happening. So for example, the drone could look tired when it's getting out of battery. Or if you're asking the drone to do something dangerous, maybe it could just look scared. So we wanted to see, would that even work? We had no idea. We're like, okay, that sounds really exciting, but we have no idea if it's gonna work. We'll try it out. We'll see what happens. So we had a workshop, and the idea was to develop some sort of emotional state through the drone behavior. So there's a longer story about emotional state versus personality. And I'm not going to get too deep into it, but basically personality is something that takes time to understand, and emotion is something you can immediately recognize. But it's much easier to build something based on personality. So we went between one and the other. Again, you can read the paper if you want more information, but we thought about that. So we had a workshop with different designers and researchers, and just thinking about, okay, how do we animate objects? How do we think about different emotions? So we went back to the basics, and I'm actually very, very proud that I managed to use some of this in my research. But we thought about, okay, if we think about the storytelling or the folklore literature, we're able, from the behavior of these little personas, to know which one is which. Just from how they move, they don't move the same. So we thought, okay, can we actually specifically use them and encode their behavior into the drone? So we worked with the stereotypes of personality and the big five, and the idea was to create some personality models, and then from the personality to think about interaction attributes. So for example, if the drone is happy, does it go slow or does it go fast? If somebody is introvert, for example, what type of movement are they going to use? So we just used that, and we had to come to an agreement. So we basically all worked on different personality models. We then came to an agreement to what it meant. And what we realized when we started mapping the different models is that some of them were very similar. And because they were very similar, we're not sure somebody would be able to discriminate one to the other then in terms of how the drone behaves. So we ended up mapping them into 3 different ones. And then we had to implement. What does it mean for a drone to go slow? There's no research, there's no paper that tells you what is slow. My phone doesn't move. And we have results in robotics, but they don't apply. So we did a lot of trial and errors. We just implemented lots of different paths, and we just stop random people and be like, does it look fast? Does it look slow? And we'd have these drones zooming by, zoom. And people would be, yeah, it goes fast. Okay, that's gonna be fast. But that's basically how we went through just trial and errors, and we started also implementing some sort of behavior. So for example, when the drone is antisocial, it starts doing something and sometimes it just stops in the middle. And then it starts again. When the drone is happy, it starts doing it very, very fast with very big curves in the movement. When it's exhausted, sometimes you have to ask several times before it does it. It's not very compliant. And then we looked at different altitudes. So same, it's if it's exhausted, it's flying very, very low. But if it's happy, it's flying very high. So we tried to think about all of that together and having all these different control parameters. And then we had 20 participants coming in, just seeing the different movements and telling us what they thought they saw. So these are some little special movements that the drone would do. So when the drone is happy, at the end it flips to tell you it's done. Sometimes when it's tired, it just wobbles. And so, okay, so in terms of percentage, when we ask people on the adventure model, we have between 90 and 100% recognition, depending if they use 1 or 2 keywords. So we get to 100% recognition that the drone is happy. On the other ones, we get 45% on 1 keyword and 80% on 2 keywords. So it means that 80% of the time, people were able to discriminate between each of the 3, and 100% specifically on the adventure one. Those results, even with 1 keyword, are better than what was done on the first papers with facial features on robots. So it means we got as far as the first papers on facial feature just with movement. And it's pretty awesome. It's pretty amazing that just from the movement and the behavior, we get that far. People would say things like this: the excess movement is comparable to an excited dog. Again, going back to the pet metaphor. But it also means they saw there was an excess movement. They perceived it as excessive. They've never seen a drone before. They still know it's excessive. So there is some sort of deep expectation to how it should move. and it moves different, and I'm able to see that. This person says, and I love this quote, "At first, I thought it was sad, low energy, but at the end, I figured it was capable, but reluctant." It's magic. It's like they're telling us that the technology was capable, but reluctant. It's like, yeah, the drone didn't want to do it, but now it wants to do it. Wow. It's like we're really pushing the boundaries of like, I'm taking this technology actually like a pet or a person to the point that it has its own will and desires. And this is pretty amazing that just by modifying the way it flies, we can get to that. And so we really have to rethink how we build those interfaces, because right now we're not just on like touching and inputting text. We're on like a direct communication strategy. But then we have to do it right. So we found that people can recognize variations in flight path, that emotions can be recognized in the way it flies and how it behaves. And it's very promising in terms, maybe not the home, but into everyday environments. It's like, if I'm gonna have this technology around, how do I interact with it in a very natural manner? And we may be able to do it. Now I want to get back to more traditional interfaces, because this is the future, but it's gonna take a bit longer. So in the meantime, how do we create a direct interaction between people and technology? So this is another project we did. I'm gonna first show you the concept video. So this is a longer version of the video you saw before. And we just wanted to think, if I have my own personal drone and it comes with me to the park, what can I do with it and how do I interact with it? So we thought that, for example, here she could walk, and when she wants to interact with it, she can have just a very simple gesture to open a menu. And that she can use gestures to just navigate through that menu, so in a very, very simple manner. So here she selects that she wants to go to maps, and she selects she wants to go and find her friend. So now, rather than having to like follow a map, understand where she's going, she can just physically follow the drone. She doesn't have to carry anything. She can just go and follow it. When she gets to her friend, they can start playing together. So it's not like with head-mounted display where you have to like map it to one another and synchronize. They can just play. The drone can be enabling them to play. And then we thought about things like privacy. What would happen if I want to like, you know, do something but not everybody to look at it? So we thought, where's the projector? We can just project smaller on the hand. Then she can change where she projects. So here she projects on the wall, and so she can use touch. And now she goes running with the drone. And what's pretty cool here is the drone becomes like a coach. She can just go and run at the speed of the drone. It's totally different from your average technology. It can move faster, it can move slower, it can go at the speed she went yesterday, the speed of her friend, and really, really motivate her to just follow. And so here that was a concept video. So that wasn't implemented, but that's how we started. And by building this concept video, we thought about the interface, what it would look like, what would work, what would not work. Just by making it visually, we like removed a lot of options. Initially, we tried like this accordion style menu, and we realized it would have been way too difficult. So then we went for the wheel. We thought it could be an infinite wheel, could be a limited wheel. So we thought about lots of options. And then what we did for the next 2 years is we actually made it happen. And so we have this embedded projection camera system on the drone. The way it works is we have a depth camera. So it just measures the position in depth, so like a Kinect, for example. We have a Pico projector that's laser, so it's always in focus. And we have an iPod Touch. And all the computation is done on an 88-gram iPod Touch. And it's amazing. You don't need a computer, you don't need a person with anything else. You can just put a drone in front of a person and everything gets computed on the drone. This is what it looks like from the top. So here the person, so those are not synchronized, but to show you the different images of what's happening. So you can see what the sensor is seeing, how we process the image, and then what happens in terms of interface. This is what it looks like here. The interface is being built but just by coming up. Here you can see this person interacting with it. There's a bit of jitter because the drone is flying above, but it's pretty steady. And here he selects. So then we wanted to build a tour guide for Stanford campus. And one of the projects we did, so it's a map exploration. We worked with Anke Brock within Bordeaux and she was just moved to Toulouse. And basically, we started thinking about how people interact with map on digital devices and how we could like put maps onto drones, because it's not obvious how you're going to navigate a map there. And so this is, for example, a map of Stanford campus, and we wanted to have this group and give them the ability to choose their tour. So I can see what are all the all the points of interest, choose one, get more information on it, decide to add it to my tour, which it just did here, go back, and they can generate the tour by doing that. And you see it provides a lot of excitement. So what was funny here is actually when the interface worked really, really well, like there was not too much wind, it was pretty steady, people didn't like it because it's still not as good as your phone. People have very high expectations, like phones work in 100 milliseconds or less. So they really want it to work. And with drones, it takes more time. It's not that, it takes a little bit more time. With the interface, we have a really, really good ratio, but with this one, it takes a bit more time. And so what we ended up doing here is we realized that when it didn't work as good, people actually loved it. So when there was a bit more jitter, a bit more wind, people were like super satisfied when they made it work. So there was a mix of like novelty factor, wanting to use the interface, finding it really cool, because if they were doing that on a phone, only one person could really interact. When now they can do that as a group. So only one person is interacting, but all of them are informing the decision. So they really enjoyed it, but it worked better with the lag, which is crazy. And then we actually did like a little tour guide. So here the drone would fly. It would project some information about the building. So here you have an arrow pointing at the building with a photo of it, giving you some information on the ground. People could just follow it, and all of that is like fully automated. We're not touching anything. So we just launch the drone and it goes, and the person here waves, the drone shows an interface. Here it's a 4-item menu, it could be more. Depending on what they choose, they get something else displayed and they can start again. And it's all working, autonomous, no computer, everything on the drone. So it has limitation. It's only working at night. It's not perfect, but it means that in a few seconds, somebody who's never seen a drone, never interacted with one before, can actually do the whole input and output with no training on the drone. And I'm really, really satisfied by our results here. And then we did a bigger study when we had a demo. So just a couple of words to end. So right now in Israel, we started to work on a drone for search and rescue. So drones are already being used for search and rescue. It's not new. They're really useful, for example, here when there's been a flood, and actually it's very hard for people to access the terrain. So the drone can just go and scan and get a sense of what's happening. But if you think about it, and you're like stuck in a place like this one, and a drone comes at you, it could be super scary. And so even though we have the technology to support us, in some ways it may be more frightening to have the drone. And if you see the drone, you don't know if the drone has seen you. You don't know if there's someone behind the drone or if it's autonomous. You don't know if that someone has seen you. You don't know if help is coming, when help is coming. You don't get nothing. And so what we're trying to do is actually really thinking about, if I'm stuck in this type of environment and the drone comes, how am I able to create a direct communication to the drone? And maybe I'm stuck, maybe I can't use gestures, maybe I can't talk. You don't know in what situation that person is. But there should be a way for the drone to come in a non-frightening manner to the person, for the person to give some information to how well they're doing or how not well they're doing. And then you can help the rescue team triage, because then the rescue team knows there's a person there that's okay, there's a person here that really needs help. This person is going to be okay, but they need water, and the drone can come back and bring water. The drone can even go to the rescue team and come back and tell you help will come in 2 hours, 2 days. But at least people know what to expect. So really building the technology in a way that's going to support end users and not only the owner of the technology. So right now we're working with thermal cameras. So those are 2 of my students having fun with it. The thermal cameras are really exciting because they provide really accurate images. You can find people in really complex environment, which you can't always do with RGB cameras. And so this was a big chunk of our work. I'll show you one last project very, very quickly. It was just an indoor study. Opla. Let me just remove the sound. Okay, I can't remove the sound. Okay, so here what we wanted to see is very much that. It's like, how should the drone come towards you? Does it matter if it comes fast, if it comes slow, if it comes from above, if it comes from below, if it comes from behind? So we just tried all these different parameters. We looked at the research that's been done in robotics, and we looked at like what differences does it make with drones. And there's actually major differences between expectations in robotics with ground robots and what we're getting with drones. And this is just like baby steps, but there's a lot of research to be done where we're learning everything again. But we think even the size of the drone, the noise it makes, all of that is going to have an effect. But we have to start calculating this effect to really understand what's going to happen. So this is the beginnings, but we found like some pretty strong differences in terms of how the drone should come and how to make it in a way that's non-frightening, and also in a way that people understand the drone wants to communicate. Because a lot of it, people see the drone, understand there's a drone, but don't understand the drone wants to initiate conversation. And now we have the opportunity not only for people to go and decide to interact with technology, but for technology to come to you and initiate that conversation. So what we're working on is really understanding about how do I convey that the technology can initiate the conversation and that I can respond to it. So just some final thoughts. I want to bring you back to this image. So this is actually from our very first study where a person tried to actually pet a drone. He asked us during the study, can I pet it? And I was like, please don't. I really wanted him to keep his fingers. We really need to rethink interaction with mobile devices. It's going to be collocated interaction with devices that can be fully animated. And even when we started to look at foldable screens, for example, it's a very different way of thinking about technology than just an object. It's becoming animated. So the way we interact with it, the way we even think about it, the way we consider it is totally different. So I just want you to like really think about how by creating interaction techniques, you can open really the space to how technology will change our world tomorrow. Thank you very much.